कथा श्री बालकाण्ड। एक दिन नारद सत्य लोक पुगी गया, लोको गरौँ हित भनी ब्रह्मा ताही थिया पर्या चरणमा खुसी गराया पनि। क्या सोच्छौ तिमी सोध भन्छु म भनी, मर्जी भए थियो जसै ब्रह्माको करुणा बुझेर ऋषिले बिन्ती गरायो तसै। हे ब्रह्मा जति हुन् शुभाशुभ सै, सुनिरहेको छु कछु बाँकी तथापि सुन्न हिले इच्छा म यो गर्दछु। आउला जोली बखतमा प्राणी दुराचार भई स्वभाव अनेक तरहका निजका मतिमा बात कोही अरूकै गर्नन् त निन्दा पनि, अर्काको धन खानलाई अभिलाष गर्नन् असल हो भनी। कोही जन्त पर स्त्रीमा रत हुनन्, कोही त हिंसा महा देहैलाई त आत्म जान कहनन्, नास्तिक पशु झैं तहाँ। कामका चाकर झैं भएर रहनन्, स्त्रीलाई दासी मानन्, पितृ मातृलाई बुझ्यो शत्रु सरिकारी। ब्राह्मण भइकन वेद बेचिरहन्, कोही पन्था पनि मन ठुलो छ पनि भन्या सहज धन आर्जन गरौँला भनी। जाति धर्म र वै नक्षत्रीहरूमा जो छन् यी नीचहरू, शूद्रादि त तपस्वी होइरहनन्, ब्राह्मण सरीका बरु। स्त्री धेर भ्रष्ट हुनन्, पति र ससुराको द्रोह ठुलो गरी, यस्ता नष्ट कसोरी मुक्त त हुनन्, संसार सागर तरी। यो चिन्ता मनमा भयो रहिने, यो उपाय भनी आएको छु दया निधान कसरी तर्नन् सहजै पनि। यस्तालाई उपाय तर्न सजिलो कुन हो आज्ञा गरी, मेरो चित्त बुझाइ बक्सनु हवस क्याले जान्छन् तरी। नारदले दुनिया उपर गरी दया बिन्ती गरायो जसै, ब्रह्माजी पनि खुब प्रसन्न हुनुभो मर्जी भयो यो तसै। हे नारद सब पाप हर्न कनतार रामायणैले हरि, आको मुख्य उपाय छैन सबको हित यही छ अमृत सरी। शम्भु देखि सुनेर तत्व सब यो ज्ञान पार्वती गर्दछिन्, रामको नाम अपार जानी बहुतै आनन्दमा पर्दछिन्। जति गान गर्दछन् तति सहज संसार पार गर्दछन्, कालीको पनि ताप हुँदैन भय सब तिनका सहज टर्दछन्। यो सब शास्त्र विषय बडो छ रघुनाथको रूप जनाई दिन्या, जो छन् सब यी पुराणहरू यी सबमा यही मुख्य जानी लिन्या। गर्छन् कीर्तन सुन्दछन् पनि भन्या, यो पाउँछन् फल भनी, तिनको पुण्य बखान गर्न त सबै सक्दिन मैले पनि। सुन्या थिएन शिव देखि यसकी महिमा, एक श्लोक पढुन् तापनि भक्तिले यदि यो पढ्यो भने पाप छोड्छन् भनी। जो एक चित्त गएर खुसी भई गर्छन् सदा यही भन्या जीवन मुक्ति नै हुन्न र भई सरिया बना पूजा पुस्तकको गर्या पनि त फल एक अश्वमेधका सरी पाउँछन् सुनियो कहीँ पनि भन्या पाप छुट्दछन् त्यसरी जो उसका नजिक गई नमस्कारै फगत गर्दछन् त्यस सजन सब देवता बुझी बुझा गर्दछन् चारै वेद पढेर शास्त्रहरूको व्याख्यान गर्दा पनि पाइँदैन फल त पाउँछ सहज पुस्तक दिनाले कहीँ घर एकादशीमा चौसुपल्ट पुरस्चरण गरी हुना गात्रीका फल भया जसले राम नवमी उपासी खुसीले जागरण समेतै गरी यो रामायण पाठ गरोस् कि त सुनोस् तन मन यसैमा धरी त्यसले तीर्थ पिछे तुलापुर गर्यो यसमा संशय छैन जन्म सबले आनन्दमा त्यो पर्यो रामायण कन गाउन्या पुरुषको आज्ञा त इन्द्रै पनि मान्छन् श्री रघुनाथका प्रियै हुन् मान्या यिनै हुन् भनी रोज रोज यस कन पाठ गरेर जनले सत्कर्म गर्छन् जति कोही गुण फल बढ्ती मिल्छ सबको घट्दैन तिनका रति यसमा राम हृदय छ पाप हरिलिन्या कोही ब्रह्मघाती पनि शुद्धात्मा बनि जान्छ तिन दिन पढ्या गर्छन् कृपा रामधनी रोज तीन अगाडि हनुमान राखेर पाठ गर्छ जसो भोग गर्न खोज्छ सम्पूर्ण जो यो पाठ तुलसी पिपल वरिपरि गर्छन् प्रदक्षिण गरी तिनका पाप सब जन्मका जति त छन् छुट्छन् ती त्यसै घरी त्यसमा राम गीता छ झन् अति ठुलो जसको महात्म्य पनि सब जान्या शिव मात्र छन् अरू त को अन्य छ यस्तो आधा पार्वती जान्दछिन् म त सबै चौथाइ पो जान्दछु गरेर नाश नहुन पाप छैन सो मान्दछु रामले वेद गरिकन अमृत सरी लक्ष्मणलाई दिया यही पढि लिया जाइन्छ संसार तरी मार्छु कर्तव्य निरूप ठुलो इरादरी पढ्दा शिव थिए गया परशुराम दिन दिन चरमा परी पढ्दिन पार्वती राम गीता तही सुनि पागल लागि गया राम गीता तही देखि पागल नारायणै दिया मैना राम गीता त्याहरू छुट्छन् राम गीता कन पाठ गर्यो पनि भन्या निवार गर्छु गीता भनी राम गीता उपवास गरी मानिस भनी रामै सरीको भयो यही राम पढी बग्छन् ज्योति अनन्तका पद जान्छन् सहज पाल्ने धेरै पाठ गरेर हुन्छ बुझियो यसै सरीको अबर पुराण श्रुत सोरै कलामा गरौँ फेरि ठुलो भनी चित्तले सुन्दर यो यति सुन्दर पनि जान्छ सदा ध्यानमा प्यारी पार्वती जी कहीं चरणमा परी पूर्ण लोकान्गे गर्छु सुरमा राम हुन् जगतका पति रामदेखि अरू कोही छैन जनको संसार सरी जान्दछन् क्या भन्छन् ज्ञान कोही भगवान यसमा विचार खुब गरी जो खुब भया जस्ता सोन्यो पार्वती राम अनादि तस्तै जसन जगत नाना यस्तो तत्त्व नजानी मानिस सरी रामलाई जो गर्दछन् संसारका यी अनन्त तापहरू तिनैलाई सदा बादलले क्या श्री सूर्यलाई लोकता भन्छ सब सूर्य ढाक्यो भनी भगवान रूप हुन्या जनहरू मानिस पनि परमेश्वरै सकल यस सूर्यैमा पनि अन्धकार जस्तै चरामा सबै आत्मा यिनै हुन् आगो रहस्य भन्छु सुनै ताराको हर हर जब छिन्छ यो नामको सब भार हरेर रघुनाथ सीतालाई कहीँ दिनुभयो सीधे हनुमान बडा हाम्रा भक्त भया यी तत्त्व यहाँ छन् यिनलाई तिमी तत्त्व देऊ भनियो सीताले हनुमानलाई दिनुभयो जो राम हुन् ब्रह्म यिनै कि शक्ति बलि माया भन्या कि महु रामको सन्धि पाइ पनि गरिन्छ सबै यस निर्मल रघुवंशमा प्रभुजीले जो जन्म्या लिया विश्वामित्र यज्ञहरूमा जो पाप गौतम पत्नीका हरिदिया जो भाँची दिया धनु जो मैयाई बिहा गर्या सब कुरा यस्ता जो गर्भ वीर परशुरामको जो वर्ष बिहा गर्या पछि जो तावनैमा पस्या यस्ता सब काम गर्न्या भन्छन् कर्ता यिनै हुन् भनी अन्तर्यामी अनादि साक्षी थिया मेरा गुण लिँदा त लोकहरूले कर्ता भनी पो दिया यति ताही सीताजीबाट उपदेश पाइसक्या थिया जबै आफै राम प्रभु दिनुभयो हुन्छ परात्मा अनात्मा भनी आत्मा और परात्मालाई बुझदा पाइन्छ मुक्ति पनि आत्माको र परात्माको छ कति फेर त्यो एक जानी लिनु जुन जुन चिज अनात्मा मानेर छाडिदिनु सोही ज्ञान तिमी थियौ कहिकन सक्या सम्पूर्ण मैले यहाँ गरिन् पनि तहाँ हेनाथ सबै रामको लीला सुन्न मलाई मन हुन गयो यही बुझा कामको सुनोस् राम लीला भनेर म उपर माया मुदै धरी सब लीलाहरू फेर बताउनु हवस् जो छन् तिमी यो प्रेम पार्वतीको सुन शिवले प्रेम राखी जो जो हुन् सब चित्रले बताय पनि भूमि रावण भारी तिर्दै गइन् जहाँ ब्रह्मा बस्याका हामी धेरै भयो मनना नयाँ विधान चरणमा यो बिन्ती पारिन् पनि तो बिन्ती सुनि दया पनि उठ्यो यी भूमिमाथि तहाँ दौडी सरकातिर जहाँ इन्द्रादी सम्हाली भगवान प्रसन्न हुनु भई जसै प्रभुजीको ब्रह्माण्डमा पर्या भक्तिले खुगेर सिधै हातको बिन्ती गर्या हे नाथ भई विपत्ति दियो इन्द्रादिहरूको त तेज सहजमा त्यसले लियो यसलाई अब मारी बक्सनु हवस् मानिसरीका मानिसदेखि मरास भनी त वरदान दिएछु पनि ब्रह्माको यति बिन्ती सुनि भगवानको यो हुकुम
What is up, everybody? Today you're going to go from a paper to a multifunction implementation of deterministic policy grades. If you're familiar with deep deterministic policy gradings, or DDPG for short, it is a type of deep reinforcement You see, most environments actually this is the case with say like breakout or space invaders, where the agent can move left, can move left, right, shoot by fixed degree, right? In other environments, like say robotics, the robots can move a continuous amount, so it can move in to 1, -1 to +1, anything along any. This was more methods they do work particularly well in discrete environments, but cannot tackle continuous action spaces. Now, if you don't know any of this story, I'm going to give you the rundown here in a second, but for this set of tutorials, you're going to need to have installed the OpenAgent of the learning curve, which will allow us to see the actual learning doesn't handle your typical vector operations. Now, here I'll give you a little rundown. The basic idea is we have an agent that interacts with some environment and receives a reward. The reward takes place of later learning to tell the agent what is good, what is it that it is shooting for in the environment. So the attack mind over time by known as development, the actual mathematics, but just so you know, research, the algorithms are typically concerned with solving development equation, which is expected future returns, assuming it follows something called its policy. So policy is the ability of the agent to take a set of actions given some data, basically probability. Now, things happen, just killer the development equation by finding what's called the value function. The value function, or the active value defined state and set of so one of the ways state configuration in the case of target. It's okay if I take action or the actor-critic methods are slightly different. They attempt to learn directly and policy is interrogate what the output is actually given state. So these two algorithms have a number of strengths between them, and deep deterministic policy gradients is a way to marry the strengths of these two algorithms into something that does really work in continuous action spaces. You don't need to know too much more than that. Everything else you need to know I'll explain in their respective videos. The first video, you're going to get to see how I go ahead and read papers and the second video, you're going to see the implementation of both environments are in both these environments are continuous and they are an algorithm. You need particularly powerful GPU, but you do need some kind of GPU to run these, as it does take a considerably long time on a GPU. So you will need at least a like say a Maxwell class GPU or above, so something from the 700 series. Right? Unfortunately, neither of the frameworks work well with the cards. So if you have those, you have to figure out how to get the OpenCL to compile. This is a few hours of content. Drink and watch us at your level. It's best to read it in order. I actually did the videos in separate order. Get it. So I did the first, take the paper in a second. But it is best for a new audience to go from the paper video to the video. So I would like it. Leave any comments, questions, suggestions, issues down below. I'll try to address as many as possible. You can check out the code for this on my GitHub, and you can find more videos like this on my YouTube channel. Hope you enjoy it. What is up, everybody? In today's video, we're going to go from paper on deep deterministic policy gradients all the way into a functional implementation in TensorFlow. You're going to see how to go from a paper to real-world implementation. Also, grab a snack, a drink, because it's going to take a while. Let's get started. The first step in my process really isn't anything special. I just read the entirety of the paper. Of course, starting with the abstract, it tells you what the paper is about at a high level. It's just kind of an executive summary. An introduction is where the authors will do other what is going to be the need for it. The back gives us a little bit of math equations. Yet you talk too much, this will not be implementation, but it does set the stage for the mathematics you're going to be implementing, which is of course critical for any deep learning, or in this case deep reinforcement learning, paper implementation. The algorithm is in here that lay out the exact steps you need to take to implement the, right, that's why it's titled. So most carefully, and then of course they will typically give a table where they outline the actual algorithm, and oftentimes if I'm in, I will just jump to this because I've done this enough times that I can read this, what is called pseudocode. If you're not familiar with that, pseudocode is representation of computer. So we typically use that when we have a problem, and it's often used as a. So typically I'll start here reading it and then work backward by reading through the paper to see what I missed. The environments have in common that they are continuous control. So what that means is that the action space is a vector whose elements can vary on a real number line. Instead of having 3 actions, 0, 1, 2, 3, 4, 5, is the really mission behind deep is that allows us to use deep reinforcement learning to tackle these types of problems. And in today's video, we're going to go ahead and tackle the, I guess, pendulum swing up, also called the pendulum problem. Reason being is that while it would be awesome to start out with something like the bipedal walker, you never want to start out with maximum complexity. You always want to start out with a very, very small scale your way up. And the reason you're going to make mistakes, bugs, quick, very environments that quickly. So the pendulum problem has, I think, 3 elements. It's state vector and only a single action, so, or maybe it's 2 actions, I forget, but either way, it's a very small problem relative to something like the bipedal walker or many of the other environments. You could also use the continuous version of the card pole or something like that. That would be perfectly fine. I've just chosen the pendulum for this particular video because we haven't done it before. So it's in here that they give a bunch of plots of the performance of their algorithm of the various sets of constraints placed upon it and different implementations. Get an idea. And one thing you notice right away, it's always in plots because they give you a lot of visual. It's much easier to gather information from plots than it is text. You see that right away they have a scale of 1. So that's telling you its relative performance, and you have to read the paper to know relative to what. They similar form, and in here you see a whole bunch of environments they used, and there's a broad variety. I want to show that has a wide applicability, which is typical papers. They want to show that this is relevant, right? If they only showed a single environment, people reading it would say, well, that's all well and good. You can solve one environment, but what about these dozen other environments? Right? And part of the motivation behind reinforcement learning is generality. Can we real learning and biology mimics the generality of biology? One thing you notice right away is that these numbers are not actual scores. So that's one thing I kind of take note of and causes me to raise an eyebrow. So the motivation behind that. Why would the express scores in a ratio? There's a couple different reasons. One is because they want to just to make all the numbers look uniform. Maybe the people reading the paper wouldn't be familiar with each of these environments, so they don't know what a good score is, and that's a perfectly valid reason. Other possibilities they want. I don't think that's going on here, but it does make me raise my eyebrow whenever I see it. Exception is the Torx, which is the open race car simulator environment. I don't go to that on this channel. That would be a project, but that would take me a few weeks to get through. But right away you notice that they have a whole bunch of environments. These scores are all relative to 1, and 1 is the score that the agent gets on a planning algorithm, which they also detail later on. They talk more about talks about other that are shortcomings. Talk up other algorithms, talk up your own algorithm to make it sound good. You know, writing. Of course, the conclusion that's higher references. You go deep into references. If there's something that I feel I really need, I may look at a reference, but I don't really bother with them. For a PhD student, then it would behoove you to go into the references because you must be an absolute expert on the topic. And for us, we're just, hobbyists on YouTubers, so I don't go into too much depth with the background information. And the next most important bit of the paper are the experimentals, and it is in here the percent architectures for the networks. So this is where, if you saw I did the implementation of DDPG in Python in the continuous lunar lander environment, this is where I got most of it. It was almost identical. I left out some stuff from this paper, but pretty much all of it came from here. In particular, the hidden layer sizes, 400 and 300 units, as well as the initialization from uniformization of the given ranges. So just to recap, this was a really quick overview of the paper, just showing my process of what I look at. The most part of the algorithm as well as the experimental details. So, I guess the introduction. Behind it, I get the idea. It says, it basically tells us that you can't really handle continuous action spaces with DQ networks. And it says, you can discretize the state space, really huge actions. Sorry, you can discretize action space, but then you end up with actions, what is it, 2,187 actions, so it's intractable anyway. And they say what we present, and then it comes down to this section where it says the network is policy with samples from a replay buffer to minimize correlations, very good, and train with the target Q network to give it consistent during temporal. So in this, we're going to make use of ideas along with batch normalization. So chunk of text, and this is why you want to read, because sometimes it'll embed stuff in there that you may not otherwise catch. So as I'm reading the paper, and you can do this in paper, you can do it in a text document. In this case, we're using the editor, so that way I can show you what's going on. And it's a natural place to put this stuff because that's where you're going to implement the code anyway. Let's hop over to the editor, and you'll see what I take notes. So right off the bat, we always want to be thinking in terms of what sort of classes and functions will we need to implement this algorithm. So the paper mentioned a replay buffer as well as a target queue network. So the target queue network, for now, we don't really know what it's going to be, but we can write it down. So we'll say we'll need a replay buffer class and need a class for a target queue network. Now, I would assume that if you're going to be implementing a paper of this advanced difficulty, you'd already be familiar with Q-learning, where you know that the target network is just another instance of a generalized network. The difference between the target and evaluation networks are, the way in which you update their weights. So right off the bat, we know that we're going to have a single class, at least one. If you know something about actor-critic methods, you'll know that you'll probably have two different classes, one for an actor, one for a critic, because those two architectures are generally a little bit different. But what do we know about Q networks? We know that Q networks are state action value functions, right? They're not just value functions. So the critic in the actor-critic methods is just a state value function in general, whereas here we have a Q network, which is going to be a function of the state and action. So we know that it's a function of S and A. So we know right off the bat it's not the same as a critic. It's a little bit different. And it also said we will use batch norm. So batch normalization is just a way of normalizing inputs to prevent divergence in a model. I think it was discovered in 2015, 2014, something like that. So that we use that. So we'll need that in our network. So we know, at least right off the bat, a little bit of an idea of what the network is going to look like. So let's go back to the paper and see what other little bits of information we can glean from the text before we take a look at the algorithm. Reading along, say, they say a key feature is simplicity. It requires only a straightforward actor-critic architecture and very few moving parts. And then they talk it up and say it can learn policies that exceed the performance of the planner, the planning algorithm, even learning from pixels, which we won't get to in this particular implementation. Structure of the algorithm. So this is really important if you want to have a really deep depth knowledge of the topic. If you already know enough about the background, you would know that the formula for discounted future rewards, you should know that if you've done a whole bunch of reinforcement learning algorithms. If you haven't, then definitely read through this section to get the full idea of the background and the motivation behind the mathematics. Other thing to note is it says the action value function is used in many algorithms. We know that from and then it talks about the recursive relationship known as the Bellman equation. That is known as well. Other thing to note, what's interesting here, and this is the next nugget, is if the target policy is deterministic, we can describe it as a function mu. And so you see that in the remainder of the paper, they do indeed mu this parameter mu. So that tells us right off the bat. Now, you can say from the title, right? Deterministic policy gradients, right? So you would guess from the name that the policy is deterministic. But what does that mean exactly? So policy is one in which software maps the probability of taking an action to a given state. So you input a set of state and out comes a probability of selecting an action, and you select an action according to that probability distribution. So that right away bakes in a solution to the explore-exploit dilemma, so long as all probabilities are finite, right? So as long as a probability of taking an action for all states doesn't go to zero, there is some element of exploration involved in that algorithm. Q-learning handles the explore-exploit dilemma by using epsilon selection, where you have a random parameter that tells you how often to select a random number, a random action, and then you select a greedy action the remainder of the time. Of course, policy gradients don't work that way. They typically use a stochastic policy, but in this case we have a deterministic policy, so you have to wonder right away, okay, we have a deterministic policy, how are we going to handle the explore-exploit dilemma? So let's go back to our text editor and make a note of that. So we just want to say that the policy is deterministic, how to handle explore, exploit. And that's a critical question, right? Because if you only take what are perceived as the greedy actions, you never get a really good coverage of the parameter space of the problem, and you're going to converge on a suboptimal strategy. So this is a critical question we have to answer in the paper. So let's head back to the paper and see how they handle it. So we're back in the paper, and you can see the reason they introduced that deterministic policy is to avoid an inner expectation, or maybe that's just a byproduct. I guess it's not accurate to say that's the reason they do it. But what's neat is it says the expectation depends only on the environment. It means it's possible to learn Q to the mu, meaning Q is a function of mu, off policy, using transitions which are generated from a different stochastic policy beta. So right there we have off policy learning, which is say explicitly with a stochastic policy. So we are actually going to have two different policies in this case. So then this already answers the question of how we go from a deterministic policy to solving the explore-exploit dilemma, and the reason is that we're using a stochastic policy to learn the greedy policy, or a purely deterministic policy. And of course they talk about the parallels with Q-learning. There are many between the two algorithms, and you get to the loss function, which is of course critical to the algorithm, and this y of t parameter. Then of course they talk about what Q-learning has been used for. They make mention of deep neural networks, which is of course what we're going to be using. That's where the deep comes from. It talks about the Atari games, which we've talked about on this channel as well. And importantly, they say the two changes that they introduced in Q-learning, which is the concept of the replay buffer and that's the target network, which of course they already mentioned before. They're just reiterating and reinforcing what they said. That's why we want to read the introduction and background type material to get a solid idea of what's going to happen. So now we get to the algorithmic, and this is where they again reiterate that it's not possible to apply Q-learning to continuous action spaces. Reasons, right? It's pretty obvious. You have an infinite number of actions. That's then they talk about the deterministic policy gradient algorithm, which we're not going to go too deep into, right? For this video, we don't want to do a thesis. We don't want to do a full doctoral dissertation on the field. We just want to know how to implement it and get moving. So this goes through and gives you an update for the gradient of this parameter j, and gives it in terms of the gradient of q, which is the state action value function, and the gradient of the policy, the deterministic policy mu. Other thing to note here is that these gradients are over two different parameters. So the gradient of q is with respect to the actions, such that the action A equals mu of s of t. So what this tells you is that q is actually a function, not just of the state, but is intimately related to that policy mu. So it's not an action chosen according to an argmax, for instance. It's an action chosen according to the output of the other network. And for the update of mu, it's just the gradient with respect to the weights, which you would kind of expect. So they talk about another algorithm, NFQCA. I don't know what that is, honestly. Mini batch version, blah, blah, blah. Our contribution here is to provide modifications to DBG inspired by the success of DQN. which allow it to use neural network function approximators to learn in large state and action spaces online. We call it DDP. As they say again, we use a replay buffer to address the correlations between samples generated on sequence steps within an episode. Finite size cache size R. Transition sample from the environment. So we know also, if you don't know, what you need to know here is that you have state, action, reward, and then transition. So what this tells the agent is some state S, receive some reward, and ended up in some new state. Why is that important? Because in anything that isn't dynamic state probability distributions, you're trying to from one state to another reward along the way. If you knew all of those beforehand, then you could just simply solve a very, very large set of equations, for that matter, to arrive at the optimal solution, right? If you knew all those transitions, you say, okay, if I start in this state and take some action, I'm going to end up. Then you would say, well, what's the most? What rate is going to give me the largest reward? You could kind of construct an algorithm for traversing that set of equations to maximize your reward over time. Now, of course, you often don't know that, and that's the point. The replay buffer is to learn that through experience and interacting with the environment. And it says when the replay buffer was full, the samples were started. Okay, that makes sense. It's finite. It doesn't grow indefinitely. At each time step, actor and critic are updated by sampling a mini batch uniformly from the buffer. So it operates exactly according to Q-learning. It does a uniform sampling, random sampling of the buffer that to update the actor and critic networks. What's critical here is that combining this statement with the previous paragraph is that when we write our replay buffer class, it sample state at random. So what that means is you want to sample a sequence of subsequent steps. And the reason is that there are large correlations between those steps, right, as you might imagine, and those correlations cause you to get total randomized, really cause your algorithm. So you want to sample that uniformly, sampling across many, many different episodes to get a really good idea of the, I guess, the breadth of the parameter space, to use kind of loose language. Neural networks prove to be unstable in many environments. They're going to talk about using the target network. Actor critic soft target rather than directly copying the weights. So in Q-learning, we directly copy the weights from the evaluation to the target network. Here it says we create a copy of the critic networks, Q prime and mu prime, respectively, that are used for calculating the target values. These target networks are then and slowly track the learned networks. Time goes to theta times tau plus 1 minus tau times theta prime, with tau much, much less than 1. Values are constrained to change slowly, greatly improving the stability of learning. Okay, so this is our next little nugget. So let's head over to the paper and make text editor and make note of that. What we read was that we have two, not in caps, we don't want to shout, we have two networks, target networks, sorry, we have two actor and two critic networks, a target for each. Updates are soft according to theta equals tau times theta plus 1 minus tau times theta prime. So, sorry, this should be theta prime. So this is the update rule for the parameters of our target networks. And we have two target networks, one for the actor and one for the critic. So we have a total of 4 deep neural networks. And so this is why the algorithm runs so slowly, even on my beastly rig. It runs quite slowly, even in the lunar lander, continuous lunar lander environment. I've done the bipedal walker, and it took about 20,000 games to get something that approximates a decent score. So this is a very, very slow algorithm. And that 20,000 games took, I think, about a day to run. So quite slow, but nonetheless quite powerful. It's the only method we have so far of implementing deep reinforcement learning and continuous control environments. So hey, beggars can't be choosers, right? But we know, just to recap, that we're going to use 4 networks, 2 that are on policy and 2 off policy, and the updates are going to be soft with tau much less than 1. If you're not familiar with mathematics, this double less than or double greater than sign means much less than or much greater than, respectively. So what that means is that tau is going to be of order 0.01 or smaller, right? 0.1 isn't much smaller, that's kind of smaller. 0.01 I would consider much smaller. We'll see in the details, we'll see what value they use, but you should know that it's of order 0.01 or smaller. And the reason they do this is to allow the updates to happen very slowly to get good conversions, as they said in the paper. So let's head back to the paper and see what other nuggets we can glean before getting to the outline of the algorithm. And then in the very next sentence, in the action value function closer to the case of supervised learning, a problem for which a robust solution exists. Timing Q is required to have stable targets yi and consistently train a critic. This may slow learning since investigation of value estimates, however, by the stability of learning. We'll get a lot of divergence, but it does take learning in low-dimensional and high environments, and they do that to talk for feature scaling, which to the problem is the ranges of variations in parameters, right? So in different environments, like in the mountain car, you can go from plus minus 1.6, like minus 1.6 to 0.4, and the velocities are plus minus 0.07. So you have a 2-order magnitude variation there in the parameters. That's kind of large, even in that environment. And then when you compare that to other environments, you have parameters that are hundreds, you see that there's a pretty big issue with scaling of the experience. Neural network are highly sensitive to this between inputs. So their solution to that problem is to manually scale the feature so they're similar across environments and units. And they do that by using and it says this technique normalizes each dimension of the batch to have unit, mean, and variance. And running average of the mean and variance used for normalization and evaluation. So training and testing are slightly different from supervised learning. So in supervised learning, you maintain different data sets or shuffled sets of a single data to do training and evaluation phase. You perform you just see how it does on the training. In reinforcement learning, you can do something similar where you train the agent to achieve some set of results and allow it to just choose actions based upon whatever policy. And if you're using batch normalization, in Python in particular, there are significant differences in how to use the 2 different phases, so you have to be explicit in set training or evaluation mode. PyTorch, they don't track, which is why when we wrote DDPG algorithm in Python and train functions so often. We've already established we'll need batch normalization, so everything's we need a replay network, batch normalization, we need 4 networks, right? We need 2 each of a target of an actor and 2 each of a. So half of those are going to be used for on policy, and half of them are going to be for off policy. It says, scroll down, a major learning in continuous action spaces exploration. An advantage of off-policy algorithms such as DDPG is that we can treat the problem of exploration independently from the algorithm. We constructed an exploration policy mu prime, adding noise sampled from an actor policy. Right here is what the target actor function is. It's basically mu plus some noise, and can be chosen to suit the environment and detailed in the supplementary used an Ornstein-Uhlenbeck process to generate a temporally correlated operation for exploration efficiency and physical control problems. If you're not familiar with physics, inertia just means you see if stuff stay in motion. It has environments that move, like the walker, stuff like that. So we've got one other nugget to add to our text editor. Let's head back over there and write that down. Okay, so the target actor is just the evaluation, we'll call it that for lack of a better word, evaluation actor, plus some noise process. They used Ornstein Uhlenbeck. I don't think I spelled that correctly. We'll need to look that up. That I've already looked it up. My background is in physics, so it made sense to me. It's basically a noise process that models the motion of Brownian particles, which are just particles that move around under the influence of their interaction with other particles in some type of medium, like a lossless medium, like a perfect fluid or something like that. And in the Ornstein-Uhlenbeck case, they are temporally correlated, meaning each time step is related to the time step prior to it. And I hadn't thought about it before, but that's probably important for the case of Markov decision processes, right? So in MDPs, the current state is only related to the prior state in the action taken. You don't need to know the full history of the environment. So I wonder if that was chosen that way, if there's some underlying physical reason for that. Just kind of a question that occurs to me off the top of my head. I don't know the answer to that. If someone knows, drop the answer in the comments. I would be very curious to see the answer. So we have enough nuggets here. So just to summarize, we need a replay buffer class. We'll also need a class for the noise, right? So we'll need a class for noise, a class for the replay buffer. We'll need a class for the target queue network, and we're going to use batch normalization. The policy will be deterministic, so what that means in practice is that the policy will output the actual actions instead of the probability of selecting the actions. So the policy will be limited by whatever the action space of the environment is, so we'll need some way of taking that into account. So deterministic policy means outputs the actual action instead of a probability. We'll need a way to bound the actions to the environment limits. And of course, these notes don't make it into the final code. These are just kind of things you think of as you are reading the paper. You would want to put all your questions here. I don't have questions since I've already implemented it, but this is kind of my thought process as I went through it the first time. As best as I can model it after having finished the problem. And you can also use a sheet of paper. There's some kind of magic about writing stuff down on paper, but we're going to use the code editor because I don't want to use an overhead projector to show you guys a friggin' sheet of paper. This isn't grade school here. So let's head back to the paper and take a look at the actual algorithm to get some real sense of what we're going to be implementing. The results really aren't super important to us yet. We will use that later on if we want to debug the model performance, but the fact that they express it relative to a planning algorithm makes it difficult, right? So, scroll down to the data. So, they give another thing that I didn't talk about this earlier, but I guess now is a good time, is the stipulations on this performance data. It says, performance after training across all environments for at most 2.5 million steps. So I said earlier I had to train the bipedal walker for around 20,000 games. That's around I think that's around about 2.5 million steps or so. I think it was actually on 15,000 steps, so maybe around 3 million steps, something like that. We report both the average and best observed across 5 runs. So why would they use 5 runs? So if this was a super duper algorithm, and which none of them are, this isn't a slight on their algorithm, this isn't meant to be snarky or anything. What it tells us is that they had to use 5 runs because there is some element of chance involved. So, you know, in one problem with deep learning, the problem of replicability, right? It's hard to replicate other people's results, particularly if you use system clocks as seeds for random number generators, right? Using the system clock to seed the random number generator guarantees that if you run the simulation at even a millisecond later, right, that you're going to get different results because you're going to be starting with different sets of parameters. Now, you will get qualitatively similar results, right? You'll be able to repeat the the general idea of the experiments, but you won't get the exact same results. It's kind of it's an objection to the whole deep learning phenomenon. It makes it kind of not scientific, but whatever, it works. Has enormous success, so we won't quibble about semantics or philosophical problems, but we just need to know, for our purposes, that even these people that invented the algorithm had to run it several times to get some idea of what was going to happen because the algorithm is inherently probabilistic, and so they report averages and best case scenarios. So that's another little tidbit, and they included results for both the low dimensional cases where you receive just a state vector from the environment as well as the pixel inputs. We won't be dealing with pixel inputs for this particular video, but maybe we'll get to them later. I'm trying to work on that as well. So these are the results, and the interesting tidbit here is that it's probabilistic. It's going to take 5 runs. That was like but that's not really our concern at the moment. So now we have a series of questions. We have answers to all those questions. We know how we're going to handle the explore-exploit dilemma. We know the purpose of the target networks. We know how we're going to handle the noise. We know how we're going to handle the replay buffer. And we know what the policy actually is going to be. It's the actual actions the agent is going to take. So we know a whole bunch of stuff. So it's time to look at the algorithm and see how we fill in all the details. So randomly initialize a critic network and actor network with weights theta, super Q, theta, super mu. So this is handled by whatever library you use. You don't have to manually initialize weights, but we do know from the supplemental materials that they do constrain these updates to be within, these initializations to be within some range. So put a note in the back of your mind that you're going to have to constrain these a little bit. And then it says initialize target network Q prime and mu prime with weights that are equal to the original network. So theta super Q prime gets initialized with theta super Q, and theta mu prime gets initialized with theta super mu. So we will be updating the weights right off the bat for the target networks with the evaluation networks. And initialize a replay buffer R. Now this is an interesting question. How do you initialize that replay buffer? So I've used a couple different methods. You can just initialize it with all zeros, and then if you do that, when you perform the learning, you want to make sure that you have a number of memories that are greater than or equal to the mini batch size of your training, so that way you're not sampling the same states more than once, right? If you have 64 memories in a batch that you want to sample, but you only have 10 memories in your replay buffer, then you're going to sample, let's say 16 memories, and you're going to sample each of those memories 4 times, right? So then that's no good. So the question becomes, if you initialize your replay buffer with zeros, then you have to make sure that you don't learn until you exit the warm-up period, where the warm-up period is just a number of steps equal to your replay buffer, your buffer sample size. Or you can initialize it with the actual environmental play. Now this takes quite a long time. The replay buffers are order 1 million, so if you let the algorithm take 1 million steps at random, then it's going to take a long time. I always use zeros, and then just wait until the agent fills up the mini batch size of memories. Just a minor detail there. Then it says, for some number of episodes do, so a for loop, initialize a random process N for action exploration. So this is something, now reading it, I actually made a little bit of a mistake. So in my previous implementation, I didn't reset the noise process at the top of every episode. So it's explicit here. I must have missed that line. And I've looked at other people's code. Some do, some don't. But it worked within, how many episodes was it? Within under 1,000 episodes, the agent managed to beat the continuous lunar lander environment. So is that critical? Maybe not. And I think I mentioned that in the video. Receiver initial state observation S1. So for each step of the episode, T equals 1 to capital T do. Select the action A sub T equals mu, the policy plus n sub t according to the current policy and exploration noise. Okay, so that's straightforward. Just feed the state forward. What does that mean? It means feed the state forward through the network, receive the vector output of the action, and add some noise to it. Okay. Execute that action and receive and observe reward and new state. Simple. Store that transition, the old state, action, reward, and new state in your replay buffer R. Okay, that's straightforward. Each time step, sample a random mini batch of n transitions from the replay buffer. And then you want to use that set of transitions to set y sub I equals, so I is, sorry, I'm having difficulties here. So I is each step of that, is each element of that mini batch of transitions. So you want to basically loop over that set or do a vectorized implementation. Looping is more straightforward. That's what I do. I always opt for the most straightforward and not necessarily most efficient way of doing things the first time through, because you want to get it working first and worry about implementation, efficiency later. So set y sub I equals r sub I plus gamma, where gamma is your discount factor, times q prime of the new state as sub I plus 1 times, where the action is chosen according to mu prime, given some weights theta super mu prime and theta super q prime. So what's important here is that, and this isn't immediately clear if you're reading this for the first time, this is a very important detail. So it's the action must be chosen according to the target actor network. So you actually have Q as a function of the state as well as the output, of another network. That's very important. Update the critic by minimizing the loss, basically a weighted average of that y sub I minus the output from the actual Q network, where the A sub I's are from the actions you actually took during the course of the episode. So this A sub I is from the replay buffer, and these actions, right, are chosen according to the target actor network. So for each learning step, you're going to have to do a feed forward pass of not just this target Q network, but also the target actor network, as well as the evaluation critic network. I hope I said that right. So the feed forward pass of the target critic network, as well as the target actor network, and the evaluation critic network as well. And then it says, update the actor policy using the sample policy gradient. Now, this is the hardest step in the whole thing. This is the most confusing part. So it says the gradient is equal to 1 over n times the sum. So a mean, basically, whenever you see 1 over n times the sum, that's a mean. The gradient with respect to actions of Q, where the actions are chosen according to the policy mu of the current states S, times the gradient with respect to the weights of mu, where you just input the set of states. Okay, so that'll be a little bit tricky to implement. So, and this is part of the reason I chose TensorFlow for this particular video, is because TensorFlow allows us to calculate gradients explicitly. In PyTorch, you may have noticed that all I did was set Q to be a function of the current state as well as the actor network. And so I allowed PyTorch to handle the chain rule. This is effectively a chain rule. So let's scroll up a little bit to look at that. Is that right? This is the hardest part to implement. Scroll up, you see that this is here, right? In reference to this. So it's a gradient with the weights, theta super mu, of Q of S and A, such that you're choosing an action A according to the policy mu. So really what this is the chain rule. So it's the this gradient is proportional to a gradient of this quantity times the gradient of the other quantity. It's just a chain rule from calculus. So in the PyTorch paper, we implemented this version. And these are equivalent. They're perfectly valid to do one or the other. So in PyTorch, we did this version. Today, we're going to do this particular version. All right. You want to update the target networks according to this salt update rule. So theta super q prime gets updated as tau times theta super q plus 1 minus tau theta super q prime, and likewise for theta super mu prime. And then you just end the two loops. So in practice, this looks very, very simple. But what do we know off the bat? We need a class for our replay network. We need a class for our noise process. We need a class for the actor and a class for the critic. Now, you could think that perhaps they're the same, but when you look at the which we're going to get to, you realize you need two separate, at least class to have networks. So you have at least three classes, and I always add in an agent class on top as kind of an interface between the environment and the deep neural networks. So that's 4. And we're going to end up with 5, but that's 4 right off the bat. So now that we know the algorithm, let's take a look at the supplemental details, supplemental information to see precisely the architectures and parameters used. So we these Adam for learning the neural network parameters with a learning rate of 10 to the minus 4 and 10 to the minus 3 for the actor and critic respectively. So they tell us the learning rates, 10 to the minus 4, 10 to the minus 3 for actor critic. For Q, the critic, we included L2 weight decay of 10 to the minus 2 and used a discount factor of gamma 0.99. So that gamma is pretty typical, but this important thing is that for Q, and only Q, not mu, we included L2 weight decay of 10 to the minus 2 and used a discount factor of gamma of 0.99. That's an important detail. For the soft target updates, we use tau equals 0.001, so 1 part in 1,000. That is indeed very, very small. Okay, fine. The neural networks use the rectified nonlinearity for all hidden layers. Okay. The final output layer of the actor was a tangent hyperbolic layer to bound the actions. Now, tangent hyperbolic goes from -1 to +1. So, in environments in which you have bounds of plus or minus 2, let's say, you're going to need a multiplicative factor. So that's just something to keep in mind. The low-dimensional networks, but that doesn't impact the tangent hyperbolic. It just means there's a multiplicative factor and they're related to your environment. The low-dimensional networks had 2 hidden layers with 400 and 300 units, respectively, about 130,000 parameters. Actions were not included until the second hidden layer of Q. So when you're calculating the critic function, Q, you aren't actually passing forward the action from the very beginning. You're including it as a separate input at the second hidden layer of Q. That's very important. That's a very important implementation detail. And this is learning from pixels. We use 3 convolution layers, which we don't need to know right now. We're not using pixels yet. And follow 2 fully connected layers. Final layer weights and biases of both the actor and critic were utilized from a uniform distribution, 3 by 10 to the minus case. This was to ensure that the initial opposite policy and value estimates were near 0. The other layers were initialized from a uniform distribution of plus or minus 1 over square root of f, where f is the fan-in of the layer. Fan-in is just the number of input units. And the other layer, I already read that. The actions were not included into the fully connected layers. That's for the convolutional case. So here, right now, I'm experiencing some confusion reading this. So, it says the other layers were initialized from uniform distributions related to the fan-in. The actions were not included into the fully connected layers. So I'm guessing, since they're talking about fully connected layers, they're talking about the pixel case, right? Because otherwise they're all fully connected. You know, it wouldn't make sense to say specify fully connected layers. So this gives me a little bit of confusion. Is the statement referring to, the way I initially interpreted it, it is referring to both cases for the state vector and pixel case. But whatever. I'm going to interpret it that way because it seemed to work. But there's ambiguity there, and this is kind of an example of how reading using at times because the wording isn't always. Maybe I'm just tired. Maybe rambling for about 50 minutes. My brain's turning to well, actually, but anyway. The match size of 64 for the low-dimensional problems and 16 on pixels, with a replay buffer of 10 to the 6. For the noise process, we probably noise in order to explore well environments that have the Hornbeck process with theta equals 0.15 and sigma equals 0.2, and it tells you what it does. All well and good. Okay, so these are the implementation details. We need 400 units and 300 units for our hidden layers. Atom optimizer, 10 to the minus 4 for the actor, 10 to the minus 3 for the critic. For the critic, we need an L2 weight decay of 10 to the minus 2, discount factor of gamma 0.99. And for the soft update factor, we need 0.001. And we need updates, we need initializations that are proportional to the 1 over the square root of fan-in for the lower layers, and plus minus 0.003, 0.003, the final output of our fully connected network. Okay, so the details are implementing the paper. That took us about 50 minutes, which is much shorter than when I read it. It took me quite a while. Head back here, and we'll for the let's go ahead and head back to our code editor and start coding this up. Start with the easy stuff first. So let's start coding. We start with probably one of the most confusing aspects of the problem of the Ornstein-Uhlenbeck action noise. Now, you can go ahead and do a Google search for it, and you'll find a Wikipedia article that talks a lot about the physical processes behind it, a lot of mathematical derivations, and it's not particularly helpful. So if you want to be a physicist, I invite you to read that and check it out. It's got some pretty cool stuff. It took me back to my grad school days, but we have a different mission in mind for the moment. The mission now is to find a code implementation of this that we can use in our problem. So if you then do a Google search for Ornstein-Uhlenbeck GitHub, as in you want to find someone's GitHub example for it, you end up with a nice example from the OpenAI baseline library that shows you the precise form of it. So let me show you that 1 second. So you can see it here in the GitHub. There is a whole class for this right here that I've highlighted, and this looks to do precisely what we want. It has previous plus a delta term and a dt term, so it looks like it's going to create correlations through this x previous term. There's a reset function to reset the noise, which we may want to use, and there's this representation, which we'll probably skip because we know what we're doing and it's not really critical for this particular application, though it would be nice if you were writing a library, as these guys were, so they included the representation method. So let's go ahead and code that up in the editor, and that will tackle our first class. So I'm going to leave the notes up there for now. They do no harm. They're just comments at the top of the file. So the first thing we'll need is to import numpy as np. We know we can go ahead and start and say import TensorFlow as tf. We're going to need TensorFlow. We may need something like OS to handle model saving, so we can go ahead and import that as well. Just a fun fact, it is considered good practice to import your system level packages first, and followed by your library packages second in numerical order, followed by your own personal code in numerical order. So that's the imports that we need to start. Let's go ahead and code up our class. We'll call it OU action noise, and that'll just be derived from the base object. So the initializer will take a mu, a sigma. Now they said they used a default value of, I believe, 0.15 and a theta of 0.2. A dt term, something like 1 by 10 to the minus 2. And our x naught we'll save as none. And again, if you have any doubts on that, just go check out the OpenAI baselines for it. Their implementation is probably correct, right? I'll give them the benefit of the doubt. So go ahead and save your parameters as usual. So we have a mu, a theta, a dt, a sigma, an x0, and we'll go ahead and call the reset function at the top. Now they override the call method, and what this does is it enables you to say noise equals OU action noise, and then when you want to get the noise, you would just say our noise equals noise. You can use the parentheses. That's what overriding call does. That's a good little tidbit to know. So we want to implement the equation that they gave us. It's self.xPrevious plus self.theta times mu minus xPrevious times self.dt plus sigma times numpy dot square root self.dt times numpy random normal with a size of mu. And set the xPrevious to the current value. That's how you create the temporal correlations and return the value of the noise. So we don't have a value for xPrevious, so we have to set that with the reset function, which takes no parameters. Self.xPrevious equals x naught if self.x naught is not none, else numpy zeros like self.mu. And that's it for the noise function. That's pretty straightforward. So that's all well and good. So we have one function down. So we've taken care of the noise. Sorry, one class down. We've taken care of the noise, and now we can move on to the replay buffer. So this will be something similar to what I've implemented in the past. There are many different implementations and ways of implementing this. Many people use a built-in Python data structure called a DQ or a DEC. I think it's DQ is the pronunciation. Basically, it's a queue that you fill up over time, and that's perfectly valid. You can do that. There's no reason not to. I prefer using a set of arrays and using NumPy to facilitate that. The reason being that we can tightly control the data types of the stuff that we're saving. For this pendulum environment, it doesn't really matter, but as you get more involved in this field, you will see that you are saving stuff that has varying sizes. So if you're trying to save images, let's say, from one of the Atari libraries or a Mujoko environment or something like that, I hope I pronounced that correctly, you'll see that this memory can explode quite quickly and eat into your RAM. So the ability to manipulate the underlying data type representation, whether you want to use single or double precision for either your floating point numbers or your integers, is critical to memory management, as well as taking advantage of some other optimizations for NVIDIA GPUs in the Turing class and above. So I always use the NumPy arrays because it's a clean implementation that allows manipulation of data types. You can use the DQ if you want. It's perfectly valid. So our separate class has its own initializer, of course. So we're going to want to pass in a maximum size, the input shape, and the number of actions, right? Because we have to store the state, action, reward, and new state tuples. We're also going to want to facilitate the use of the done flag, so we'll have an extra parameter in here. And the reason behind that is intimately related to how the Bellman equation is calculated. It took me a second to think of that. At the end of the episode, the agent receives no further rewards, and so the expected future reward, the discounted future reward, if you will, is identically 0. So you have to multiply the reward for the next state by 0 if that next state follows the terminal state. If your current state is terminal, then the next state is following the terminal state, so you don't want to take into account anything from that, the expected future rewards, because they're identically 0. So we need a done flag is all I wanted to say. So we save our parameters. We don't even need to save that. We can say self.mem counter equals 0, and that'll keep track of the position of our most recently saved memory. State memory, an array of numpy zeros, mem size by input shape, new state memory, same deal, it's just totally the same. Good grief. Okay, so now we have the, let's say, action memory, and that's numpy zeros, self.mem size by self.nActions. We didn't save nActions, did we? So we'll just call it nActions. We have the reward memory, and that's just a scalar value. So that only gets shape self-mem size. We also need the terminal memory. Terminal memory, and that'll be shape self.mem size. and I have a NumPy float32. If I recall correctly, that is due to the data types in the PyTorch implementation. Is probably not necessary here in the TensorFlow implementation, but I left it the same way just to be consistent. It doesn't hurt anything. So next we need a function to store a current transition. So that'll take a state, action, reward, new state, and a done flag as input. So the index of where we want to store that memory is the memory counter modulus the mem size. So for any mem counter less than mem size, this just returns mem counter. For anything larger than mem size, it just wraps around. So if you have 1,000,000 memories all the way up from 0 to 999,999, it will be that number, and then once it's 1,000,000, it wraps back around to 0, and then 1, and 2, and so on, and so forth. And so that way you're overriding memories at the earliest part of the array with the newest memories, precisely as they describe in the paper. If you're using the DQ method, then I believe you would just pop it off of the left, I believe. Don't quote me because I haven't really used that implementation, but from what I've read, that's how it operates. New state memory, subindex equals state underscore reward memory equals subindex reward as action memory. Now keep in mind that the actions in this case are arrays themselves, so it's an array of arrays. Just keep that in the back of your mind so that you can visualize the problem I'm trying to solve here. Next up we have the terminal memory. Now a little twist here is that we want this to be 1 minus int of done. So done is either true or false, so you don't want to count the rewards after the episode has ended. So when done is true, you want to multiply by 0. So 1 minus int of true is 1 minus 1, which is 0. And when it's not over, it's 1 minus 0, which is just 1. So that's precisely the behavior we want. And finally, you want to increment mem counter by 1 every time you store new memory. Next, we need a function to sample our buffer, and we want to pass in a batch size. Alternatively, you could make batch size a member variable of this class. It's not really a big deal. I just did it this way for whatever reason I chose to do it that way. So what we want to do is we want to find the minimum either. So let's back up for a second. So what we want is to sample the memories from either the 0th position all the way up to the most filled memory, the last filled memory. So if you have less than the max memory, you want to go from 0 to mem counter. Otherwise, you want to sample anywhere in that whole interval. So max mem equals the minimum of either mem counter or mem size. And the reason you don't want to just use mem counter is that mem counter goes larger than mem size. So if you try to tell it to select something from the range mem counter when mem counter is greater than mem size, you'll end up trying to access elements of the array that aren't there, and it'll throw an error. So that's why you need this step. Next, you want to take a random choice of from 0 to max mem of size batch size. So then you just want to gather those states from the respective arrays, like so. I forgot the self, of course. New states, actions, rewards, and call it terminal batch. I believe that's everything. And you want to return the states, actions, rewards, new states, and terminal. Okay, so now we are done with the replay buffer class. So that's actually pretty straightforward. And if you've seen some of my other videos on DeepQ Learning, then you've seen pretty much the same implementation. I just typically kept it in the agent class then. I'm kind of refining my approach, getting more sophisticated over time, so it makes sense to stick it in its own class. So we're already like 40% of the way there. We got 5 classes in total, so that's good news. So next up, we have to contend with the actor and critic networks. So we'll go ahead and start with the actor. And From there, keep in mind that we have two actor networks, and we're going to have to contend with some of the peculiarities and way TensorFlow likes to do stuff. So let's get started. The actor, and of course in TensorFlow you don't derive from any particular class, or in PyTorch you would derive from nn.module. Don't know what I'm doing there. Definite. So we'll need a learning rate, number of actions, a name, and the name is there to distinguish the regular actor network from the target actor network. Input dims. We're going to want to pass it a session, so TensorFlow has the construct of the session, which houses the graph and all the variables and parameters and stuff like that. You can have each class having its own session, but it's more tidy to pass in a single session to each of the classes. Number of dimensions for the first fully connected layers, so of course that should be 400 if we're going to implement the paper precisely. FC2dims is 300. An action bound, a batch size, that defaults to 64. A checkpoint directory, and the purpose of that is to save our model. And in the case of the pendulum, it doesn't really matter because it's so quick to run, but in general you want a way of saving these models because it can take a long time to run. So we'll save our learning rate, number of actions, and all of the parameters we passed in. Dot FC1 dims. And the purpose of this action bound is to accommodate environments where the action is either greater than plus or minus -1. So if you can go from plus or minus 2, then the tangent hyperbolic is only going to sample like half your range, right, from plus minus 1. And so you want to have an action bound and there's a multiplicative factor to make sure that you can sample the full range of actions available to your agent. And we need to save that checkpoint dir. And finally, we want to call a build network function. Well, it's not final, but we'll call the build network function. Next up, since we have to do the soft cloning, the soft update rule for the target actor class and target critic, then we know that we have to find a way of keeping track of the parameters in each network. So we're going to keep track of them here in the variable params. And it's TensorFlow.trainable variables with a scope of self.name. So we have a single session, a single graph, and you're going to have multiple deep neural networks within that graph. We don't want to update the critic network when we're trying to do the actor network and vice versa, right? We want those to be independent. And so we scope them with their own name so that TensorFlow knows, hey, this is a totally different set of parameters from this one. And that'll aid in copying stuff later, and it'll also make sure that everything is nice and tidy. And the scope is what facilitates that. We'll also need a saver object to save the model. Let's make a checkpoint file, and that's where we use OS, and that will clone into checkpoint dir, and the name plus underscore ddpg.checkpoint. So this will automatically scope the save files for us, so that way we don't confuse the parameters for the target actor and actor, or critic and target critic, or even actor and critic for that matter. Very important. So we're going to have to calculate some gradients, and we're going to do that by hand. So we're going to need a series of functions that will facilitate that. And the first of which is the unnormalized actor gradients. And that is given by TensorFlow.gradients, self.mu, self.params, and minus self.action gradient. So we're going to calculate, so mu will be the mu from the paper, the actual actions of the agent. Params are our network parameters, and this action gradient. So let's go back to the paper for a second so we can get some idea what I'm talking about here. So if we look at the algorithm, we can see that we're going to need these gradients of the critic function with respect to to the actions taken. We're also going to need the gradient of the actual mu with respect to the weights of the network. So we're passing into TensorFlow gradients this function mu, the parameters to get the gradient with respect to those parameters, and then we're going to have to calculate the gradient of the critic with respect to the actions taken. So we'll have to calculate this later. That's a placeholder. That's the minus self.action gradient, and we're going to calculate that in the learning function. But that's where all of that comes from. So now let's go back to the code editor and continue. So that's our unnormalized integer gradients, and unnormalized is just because we're going to take 1 over the sum, 1 over n times the sum. We need a function for performing that normalization. So the actor gradients has to be, this parameter has to be a list, so we cast it as a list, and we're just going to map the lambda function, lambda x, tf.div, x, and batch size. No big deal there. So optimize is our optimization step. And of course, that's the Atom optimizer. We want to optimize with the learning rate of self.learning rate, and we want to apply gradients. So typically you would use .minimize loss, but in this case we're calculating our gradients manually, so we need to apply those gradients. And what do we want to apply? We want to apply the actor gradients to the params. And I would encourage you to go look at the TensorFlow code for all of these. The video is getting a little bit long. We're already up to like an hour and 10, 20 minutes, something like that. So I'm not going to go through all the documentation for TensorFlow. Feel free to look that up. I had to when I was building this out. So next up, we need to build our network. So this is how we're going to handle the scoping. tf.variable underscore scope self.names. That way every network gets its own scope. We need a placeholder for the input. That'll be 32-bit floating number. Shape of none, which is batch size. Input dims and dioms. That won't work. Let's put this on its own line. And we're going to give it a name. It's not critical. The name parameter is just for debugging. If something goes wrong, then you can kind of trace where it went wrong. Makes life a little bit easier. The action gradient is also a placeholder. That is what we're going to calculate in the learn function for the agent. And that gets a shape of none by n actions. So it'll be the gradient of q with respect to each action. So it has number of dimensions of actions. And so those are our two placeholder variables. And now we get to construct the actual network. So let's handle the initialization first. So F1 is the fan-in. It's 1 divided by numpy square root FC1 dims. And our dense 1, TF layers dense. And that takes self.input as input with self.fc1 dims as units. Our kernel initializer equals random. I forgot it in imports. It's random uniform. 1 second minus F1 to F1. And the bias initializer. Kernel. No, that's not right. Kernel. Bias initializer. Random uniform minus F1 to F1. That gets 2 parentheses. So we have to come back up to our imports. Import TensorFlow dot initializers. No. So we have to come back up here and say from TensorFlow dot initializers import random uniform. And now we're good to go. Here. We have dense 1. Now we want to do the batch normalization. So batch 1 equals TF layers batch normalization dense 1. And that doesn't get initialized. So now let's activate our first layer. That's just the ReLU activation of the batch batch normed. Now, it is an open debate, from what I've read online, about whether or not you should do the activation before or after the batch normalization. I'm in the camp of doing it after the activation after the batch norm. That's because the ReLU activation function, at least in the case of ReLU, so in ReLU you lop off everything lower than 0, so your statistics might get skewed to be positive instead of maybe they're 0, maybe they're negative, who knows. So I think the batch norm is probably best before the activation, and indeed this works out. This is something you can play with, so go ahead and fork this repo and play around with it and see how much of a difference it makes for you. Maybe I missed something when I tried to do it the other way. It's entirely possible I miss stuff all the time. So it's something you can improve upon. That's how I chose to do it. And it seems to work, and who knows, maybe other implementations work as well. So now let's add some space. So F2 is 1 over square root ST2 dims. Dins2 is similar. That takes layer 1 activation as input with ST2 dims. We don't need that. I'm going to come up here and copy this. There we go, except we have to change F1 to F2. Perfect. Then we have batch 2. And that takes dems2 as input. Layer 2 activation. Batch 2. Now finally, we have the output layer, which is the actual policy of our agent, the deterministic policy, of course. And from the paper, that gets initialized with the value of 0.003. And we're going to call this mu. That gets layer 2 activation as input. And that needs an actions as the number of output units. What's our activation? That is tangent hyperbolic, tanh. And I will go ahead and copy the initializers here. Of course, that gets F3, not F2. Perfect. Can I tab that? I can. Okay. So that is mu. And then we want to take into account the fact that our environment may very well require actions that have values plus greater than plus or minus 1. So self.mu is tf.multiply with mu and the action bound. And action bound will be, something like 2. It needs to be positive, so that way you don't flip the actions. But that's pretty straightforward. So now we've built our network. Next thing we need is a way of getting the actual actions out of the network. So we have a prediction function that takes some inputs, and you want to return self.sess.run self.mu with a feed dictionary of self.input and pass in inputs. That's all that is there is to doing the feed forward. Kind of an interesting contrast to how PyTorch does it with the explicit construction of the feed forward function. It just runs a session on this and then goes back and finds all the associations between variables. Nice and simple. Function to train. Now take inputs and gradients. This is what will perform the actual backpropagation through the network. And you want to run self.optimize. That's our function that accommodates learning, with a feed dictionary of inputs, and self.action gradients. So that is also reasonably straightforward. So, let's format that a little bit better. All right, so that is our training function. Next, we need 2 functions to accommodate the loading and the saving of the model. So, define save checkpoint, print. Then you want to say self.saver.save, very creative. You want to save the current session to the checkpoint file. And the load checkpoint function is the same thing, just in reverse. So here we want to print loading checkpoint self.saver.restore that session and the checkpoint file. So that will, you can only call this after instantiating the agent, so it will have a default session with some initialized values, and you want to load the variables from the checkpoint file into that checkpoint. And that is it for the actor classes. Here's the actor gradients, and this is just two functions that accommodate the fact that we're going to manually calculate the gradient of the critic with respect to the actions taken. So let's go ahead and do the critic class next. That is also very similar, so that again derives from the base object, gets an initializer, and it's pretty much the same number of actions, a name, input dims, a session, SE1 dims, SE2 dims, a batch size will default to 64, and a checkpointer will default to this. Just a note, you have to do a make dir on this temp/ddpg first, otherwise it'll bark at you. Not a big deal, just something to be aware of. Since it's identical, let's go ahead and copy here. Exactly the same, all of this. Now we need the checkpoint file, let's grab that. Control C, here, Control V, voila, it is all the same. So very straightforward, nothing too magical about that. So now let's handle the optimizer. Because we've already called the function to build our network, we can define our optimizer. So self.optimize, tftrain.add an optimizer, and we're going to minimize the loss, which we will calculate in the build network function. And we also need the function to actually calculate the gradients of Q with respect to A. So we have self.action gradients, self.q, and actions. Let's build our network. With TF variable scope, self.name. So now we need our placeholders again. We need self.input, placeholder, float 32. We need a shape none by input dims. Now, if you're not too familiar with TensorFlow, specifying none in the first dimension tells TensorFlow you're going to have some type of batch of inputs, and you don't know what that batch size will be beforehand, so just expect anything. And let's delete that, say, oh, we need a comma for sure, and say name equals inputs. Here we go. Did I forget a comma up here? So we need the actions, because remember we only take into account the actions on the second hidden layer of the critic neural network. I have float 342, shape none by and actions, name of actions. Now, much like with Q-learning, we have a target value. Let me just go back to the paper really quick and show you what that precisely will be. So that target value will be this quantity here, and we will calculate that in the learning function as we get to the agent class. So let's go back to the code editor and finish this up. So QTarget is just another placeholder, and that's a floating point number. None by 1, it's a scalar, so it is shape batch size by 1, and we will call it targets. Okay, so now we have a pretty similar setup to the actor network. So let's go ahead and come up here and No, not all of that, just this. And come back down here. So F1 we recognize that's just the fan in. We have a dense layer for the inputs, and we want to initialize that with a random number. Pretty straightforward. Then we can come up to F2 and copy that as well. So the second layers, it'll be a little bit different, but we'll handle that early. So now F2, the layer 2 is pretty similar. The only real difference is that we want to get rid of that activation. And the reason we want to get rid of that activation is because after we do the batch norm, we have to take into account the actions. So we need another layer. So action in, CF layer is dense. It's going to take in self.actions, which will pass in from the learning function. And that's going to output FC2 dims with a ReLU activation. So then our state actions will be the addition of the batch 2 and the action in, and then we want to go ahead and activate that. Okay, so this is something else I pointed out in my PyTorch video, where this is a point of debate with the way I've implemented this. I've done it a couple different ways. I've done the different variations, and this is what I found to work. I'm doing a double activation here. So I'm activating the ReLU. I'm doing the ReLU activation on the actions in, or on the output of that dense layer, and then I'm activating the sum. Now, the ReLU function is non-commutative with respect to the addition function, so the ReLU of the sum is different than the sum of the ReLUs, and you can prove that to yourself on a sheet of paper. But it's debatable on whether or not the way I've done it is correct. It seems to work, so I'm going to stick with it for now. Again, fork it, clone it, change it up, see how it works, and improve it for me. That would be fantastic. Then make a pull request, and I'll disseminate that to the community. So we have our state actions. Now we need to calculate the actual output of the layer, and an F3 is our uniform initializer for our final layer, which is self.q. Self.layers.dense, that takes state actions as input, outputs a single unit, and we have the initializers and boxes up here. Let's paste that. There we go. That's a little bit better. Still got a whole bunch of white space there. All right. So we are missing one thing, and that one thing is the regularizer. So as I said in the paper, they have L2 regularization on the critic. So we do that with kernel regularizer equals tf keras regularizers dot L2 with the value of 001. 01, sorry. So that is that for the Q, and notice that it outputs 1 unit, and it outputs a single unit because this is a scalar value. You want the value of the particular state action pair. Finally, we have the loss function, and that's just a mean squared error, Q target, and Q. So Q target is the placeholder up here in the learn function from the agent. Q is the output of the deep neural network. Okay, so now similar to our critic, we have a prediction function. It takes inputs and actions, and you want to return self.sess.run, self.q with a feed dictionary of self.input inputs and actions. Oops. Next, you need a training function, and that's slightly more complicated than the actor because it takes in the inputs, actions, and a target. And you want to return self.sess.run, self.optimize with a feed dictionary of self.input inputs, self.actions actions, and Q target. spacing on that's a little wonky, whatever, we'll leave it. That's a training function. Next, we need a function to get the action gradients, and that'll run that action gradients operation up above. So let's get that. Again, takes inputs and actions as input, and you want to return self.session.run self.action gradients with its own feed dictionary equals self.input inputs and self.actions actions. And then we also have the save and load check, which are to so that is it for the critic class. So now we have most of what we need. We have our replay buffer, actor, agent, and functionality. It'll house the noise, the memory, the replay buffer, as well as the 4 different deep neural networks. And that derives from the base object. Initializer is a little bit long, and that takes an alpha and a beta. These are the learning rates for the actor and critic respectively. Recall from what we read in the paper, they use 0001 and 001 for both networks. We need input dims, tau, the environment. That's how we're going to get the action bounds. A gamma of 0.99 per the paper. In this case, we need number of actions equals 2. A mem size for our memory of 1 million. Layer 1 size of 400, a layer 2 size of 300, and a batch size of 64. So of course we want to save all of our parameters. We'll need the memory, and that's just a replay buffer, max size, input dims, and number of actions. We will need a batch size. Here's where we're going to store the session, and this is so that we have a single session for all 4 networks. And I believe, don't quote me on this, but I tried it with an individual session for each network, and it was very unhappy when I was attempting to copy over parameters from one network to another. I figured there were some scoping issues, so I just simplified it by having a single session. There's no real reason that I can think of to have more than one. And that is an actor that gets alpha number of actions. The name is just actor. Input dims, the session, layer 1 size, layer 2 size, action space dot high. And that's our action bounds, the action space dot high. Next we have a critic. That gets beta and actions. Its name is just critic. Input dims, self.session, layer 1 size, layer 2 size, and we don't pass in anything about the environment there. So now we can just copy these, and instead of actor, it is target actor. And let's go ahead and clean up and be consistent with our PEP8 style guides. Always important. That actually makes you stand out. I've worked on projects where the manager was quite happy to see that I had a somewhat strict adherence to it. Just something to take note of. Then we have a target critic as well. And we will clean up. And so that is all 4 of our neural networks. That's pretty straightforward. So now we need noise. That's an OU action noise with mu equals numpy zeros in the shape and actions. So now we need operations to perform the soft updates. So The first time I tried it, I defined it as its own separate function. And that was a disaster. It was a disaster because it would get progressively slower at each update. And I don't quite know the reason for that. I just know that that's what happened. And so when I did into the initializer and defined one operation, I'm guessing it's because it adds, every time you call it, it probably adds something to the graph, so that adds overhead to the calculation. That's my guess. I don't know if that's accurate. It's just kind of how I reasoned it. But anyway, let's go ahead and define our update operations here. So what we want to do is iterate over our target critic parameters and call the assignment operation. What do we want to assign? We want to assign the product of critic params and self.tal plus give.multiply self.target critic param sub I times and no, that should be a comma and 1 minus self.tal. So we get 2. Let's do that, and that is a list comprehension for I in range length of target critic dot params. It's that. We don't need that. I don't believe. No. So then we have a similar operation for the actor. We just want to swap actor and critic. Target actor. So dot actor actor dot params. I did the same thing here, didn't I? Target actor, and up here, dot params. Okay, target actor, and then target actor. There. So now we have our soft update operations according to the paper. Finally, we have constructed all of the graphs, for the whole 4 networks. So we have to initialize our variables. Self.session.run, tf global variables initializer. You can't really run anything without initializing it. And as per the paper at the very beginning, we want to update the network parameters. At the beginning, we want to pass in we want the target networks to get updated with the full value of the evaluation networks, and so I'm passing in a parameter of first equals true. So since it's confusing, let's do that function first. Update network parameters. First will default to false. So if first, we need to say old tau equals self.tau. I need to save the old value of tau to set it again so that I can reset it. Self.tau equals 1, and say self.target critic.session.run update critic self.target actor.session.run self.update actor. And as I recall, this is important which session you use to run the update, although maybe not since I'm using only one session. If you want to play around with it, go ahead. And then go ahead and reset the tau to the old value, because you only want to do this particular update where you update the target network with the original network full values on the first term, on the first go through. Otherwise, just go ahead and run the update function. Boom. So next we need a way of storing transitions. Self, state, action, reward, new state, and done. So self.memory.store transition. You want to store all this stuff. This is just an interface from one class to another. You know, this may or may not be great computer science practice, but it works. Next, we want a way of choosing an action, and that should take a state as input. Since we have defined the input variable to be shaped batch size by n actions, you want to reshape the state to be it should be 1 by the observation space. New access all, and that's because we have the come up here for the actor network, just so we're clear. It is because this has shape none by input dims. So if you just pass in the observation vector that has shape input dims, and it's going to get uppity with you. So you have to read it because you're only passing in a single observation to determine what action to take. So mu actor.predict state noise equals self.noise, mu prime equals mu plus noise. Return sub-0, so this returns a tuple, so you want the 0th element. So now we have the learning function, and of course this is where all the magic happens. So if you have not filled up the memory, then you want to go ahead and bail out. Otherwise, you want to go ahead and sample your memory. So the memory does sample buffer batch size. So next we need to do the update from the paper. So let's go back to the paper and make sure we are clear on that. So we need to, we already sampled this, so we need to calculate this. And to do that, we're going to need the Q prime, the target critic network, as output, as well as the output from the target actor network. And then we use that to update the loss for the critic, and then we're going to need the output from the critic as well as from the actor network. So we need to basically pass states and actions through all 4 networks to get the training function, the learning function. So let's go ahead and head back to the code editor and do that. So our critic value for Q prime, so Q critic value underscore, self.target critic predict, and you want to pass in the new states, and you also want to pass in the actions that come from the target actor. New state. I need 1 extra parenthesis there. So then we want to calculate the y sub i's for the targets. So that's an empty list for j in range, self.batch size, target.append reward critic value underscore j times done sub j, and that's where the I kept harping on getting no rewards after the terminal state. That's where that comes from. When done is true, then it's 1 minus true, which is 0, so you're multiplying this quantity by 0, so you don't take into account the value of the next state, right, which is calculated up here. You only take into account the most recent reward, as you would want. So then we just want to reshape that target into something that is batch size by 1. That's to be consistent with our placeholders. And now we want to call the critic train function, right, because we have everything we need. We have the states, actions, and targets, with states and actions from the replay buffer and the target from this calculation here. Very easy. Now we need to do the actor update. So the action outs, self.actor.predict, we get the predictions from the actor for the states. Our grads, the gradients, get action, gradients, state, outs. That'll get the, remember, that'll do a feed forward and get the gradient of the critic with respect to the actions taken. And then you want to train the actor, state, and grads, the gradients. It's a tuple, so you want to dereference it and get the 0th element. And then finally, you want to update network parameters. Whew. Okay, so that is it for the learn function. Now we have two other bookkeeping functions to handle, which is save models, and this will save all of our models. So self.actor.save checkpoint, self.targetActor, save checkpoint, self.critic, and a function to load models. Sounds like a dogfight out there. So we want to load checkpoints instead of saving them. Load checkpoints, load, and load. So that is it for the agent class. It only took about an hour, so we're up to about 2 hours for the video, so longest one yet. So this is an enormous amount of work. This is already 310 lines of code. If you've made it this far, congratulations. This is no mean feat. This took me, a couple weeks to hammer through, but we went through. So this is all the way to the implementation. Now to actually test it. So let's open up a new file and save that as main tensorflow.py. And what we want to do now is go ahead and test this out in the Pendulum environment. I call it TensorFlow Original. Import the Arc agent. We need Gym. We need, do we need NumPy for this? Yes, we do. We don't need TensorFlow. From utils, import plot learning, and we don't need OS. So we will have a score history. You know what? I don't want to do that. Let's say if name equals main. Now we want to say env gym.make benju lum-v0 agent equals agent. It gets a learning rate of 0001, a beta of 01, put dims 3, equals 3, tau 01, pass in our environment, batch size 64. I'm being verbose here, and it looks like when I ran this, I actually used different layer sizes. Well, that's an issue for hyperparameter tuning. I just want to demonstrate that this works, and actions equals 1. So when I got good results for this, I actually used 800 by 600, and I cut these learning rates in half, but we'll go ahead and use the values from the paper. Sometimes I do hyperparameter tuning. Other thing we need to do is set our random seed. We can just put it here, whatever. The reason we want to do this is for replicability, and I have yet to see an implementation of this where they don't set the random seed. And I've tried it without it, and you don't get very good sampling of your replay buffer. So this seems to be a critical step, and most implementations I've seen on GitHub do the same thing. So let's go ahead and play our episodes. Say 1,000 games. env.reset. We forgot our score history, of course. That's to keep track of the scores over the course of our games. Done is false. And the score for the episode is 0. So let's play the episode. Say act, agent.choose, action, takes obs as input, new state, reward, done, info equals env.step, act, agent.remember, obs, act, reward, new state, int done. I guess the int done really isn't necessary. We take care of that in the replay buffer class, but you know, doesn't hurt to be explicit. And then we want to learn on each time step, because this is a temporal difference method. Keep track of your score and set your old state to be the new state, so that way when you choose an action on the next step, you are using the most recent information. Finally, at the end of every episode, you're going to append that score to the score history and print episode I score %.2f score 100 game average %.2f percent. I'll probably mean score history last 100 games minus 100 on one more, and at the end equals pendulum.png plot learning score history, file name, and a window of 100. The reason I chose a window of 100 is because many environments define solved as trailing 100 games over some amount. The pendulum doesn't actually have a solved amount, so what we get is actually on par with some of the best results people have on the leaderboard, so it looks like it does pretty well. So that is it for the main function. Let's go ahead and head to the terminal and see how many typos I made. Alright, here we are. Let's go ahead and run the main file. Invalid syntax. I have an extra parenthesis. I'm just going to delete that really quick. Run that. I have the star out of place. Let's go back to the code editor and handle that. So it looks like it is on line 95. It is here. Alright, back to the terminal. Let's try it again. And it says line 198, invalid syntax. Oh, it's because it's a comma instead of a colon. Alright, I'll fix that. Once more. Alright, so that was close. So actor object has no attribute input dims, line 95. Okay, that's easy. Let's head back. So it's in line 95. Just back to save input dims. And that probably means I forgot it in the critic and yes, it does. Alright, now we'll go back to the terminal. Hopefully that's the last one. Alright, moment of truth. It takes one positional argument, but 7 were given. Good grief. Okay, 1 second. So that is, of course, in line 234. 1, 2, 3, 4, 5, 6, 7 parameters. 1, 2, 3, 4, 5, 6, 7. What have I done? Oh, that's why. It's class critic, of course. Alright, let's go back to the terminal and see what happens. Name action bound is not defined. And that is in the... Okay. Line 148. That is in the critic. That's because I don't need it there. Let's delete it. That was just for the actor. It's because I cut and pasted. Always dangerous. I tried to save a few keystrokes to save my hands and ended up wasting time instead. Alright, let's go back to the terminal. Alright. No. It's 126. Self.input here. Okay. So I'll let that run for a second. I for 1,000 gains earlier, and this is the output I got. Now keep in mind it's with slightly different parameters. Here isn't that whether or not we can replicate the results, even know what the results really were, because they is a fraction of a fraction of the performance of a planning agent. So who knows what that really means? I did a little bit of hyperparameter tuning. It was double the number and half the learning rate, and with something that looks like this, you can see around 150 steps. So steps to solve, and if you check the leaderboards, it shows that that's actually a reasonable number. Some of the best environments only have 152 steps. Some of them do a little bit better. Sorry, best agents, 152 steps, or achieve a best score of 150 steps. It's pretty reasonable. So the implementation looks like it's very slow to learn. You can see how it's kind of starts out worse and then starts to get a little bit better. So that's pretty typical. You see this, oscillation in performance over time pretty frequently. But that is that. That is how you go from a paper to a full implementation in about 2 hours. Of course, it took me many times that to get up, but this, for all it's worth, this has been a tough project, so I'm going to present many more environments in the future. I may even do a video like this for PyTorch. I have yet to work on Keras implementation for that, but there are many more DDP videos too. So subscribe to make sure you don't miss, and share this if you find it helpful. That helps to you all in the we're going to code a deep deterministic policy gradient agent to beat the continuous environment in PyTorch. No prior experience needed. You don't need to know anything about deep reinforcement learning. You just have to follow along. Let's get started. Handle file operations and all of the stuff from Torch that we've come to expect, as well as NumPy. I'm not going to do a full overview. That will be in a future video where I will show you how to go from the paper to an actual implementation of deep deterministic policy gradients. So make sure you subscribe so you don't miss that. But in this video, we're just going to get the very high-level overview, the 50,000 foot view, if you will. That will be sufficient to get an agent to beat the continuous linear liner environment, so that's good enough. So the gist of this is we're going to need several different classes. So we'll need a class to encourage exploration, in other words, a type of noise. And you might have guessed that from the word deterministic. It means that the policy is deterministic and chooses some action certainty. And so if it is purely deterministic, it can't really explore, so we'll need a class to handle that. We'll also need a class to handle the replay memory, because deep deterministic policy gradients works by combining the magic of actor-critic methods with the magic of deep Q-learning, which of course has a replay buffer. And we'll also need classes for our critic and our actor, as well as the agent. So that's kind of a mouthful. We'll handle them one bit at a time, and we will start with the noise. So this class is called OU Action Noise, and the OU stands for Ornstein-Uhlenbeck. So that is a type of noise from physics that models the motion of a Brownian particle, meaning a particle subject to a random based on interactions with other nearby particles. It gives you a temporally correlated, meaning correlated in time, type of noise that centers around a mean of 0. So we're going to have a number of numbers, a mu, a sigma, a theta. If I could type, that would be fantastic, as well as a dt, as in a differential with respect to time, and an initial value that will get an original value of none. So if you want to know more about it, then just go ahead and check out the Wikipedia article, but the overview I gave you is sufficient for this tutorial. So, of course, we want to save all of our values. X0, and we want to call a reset function. So the reset function will reset the temporal correlation, which you may want to do that from time to time. Turns out it's not necessary for our particular implementation, but it is a good function to have nonetheless. So next, we're going to override the call function. If you aren't familiar with this, this allows you to say noise equals OU action noise, and then call noise. So that allows you to, instead of saying noise.getNoise, just say noise with parentheses or whatever the name of the object is. So that's overriding the call function. So we'll have an equation for that, x previous plus theta times the quantity, mu minus self.x previous times self.dt plus self.sigma times numpy square root of self dt times mp random normal size equals mu shape. So it's a type of random normal noise that is correlated in time through this mu minus x previous term. And every time you calculate a new value, you want to set the old value, the previous value, to the new one, and go ahead and return the value. So the reset function, all that does is check to make sure x0 exists. If it doesn't, it sets it equal to some zero value. So x previous equals self.x not if not none, else numpy zeros like in the shape of self.mu. That's it for the action noise. Again, this will be used in our actor class to add in some exploration noise to the action selection. Next, we need the replay buffer class, and this is pretty straightforward. It's just going to be a set of numpy arrays in the shape of the action space, the observation space, and rewards, so that way we can have a memory of events that have happened, so we can sample them during the learning step. If you haven't seen my videos on DeepQ Learning, please check those out. They will make all of this more clear, as well as checking out the videos on actor critic methods, because this, again, DDPG kind of combines actor critic with DeepQ Learning, so that will really be helpful for you. I'll go ahead and link those here as well, so that way you can get educated. So scroll down a bit. We want to save our mem size as max size. So the mem counter will start out as 0. Again, this is just going to be a set of arrays that keep track, or matrices in this case, that keep track of the state reward action transitions. And that will be in shape mem size, so our number of memories we want to store, and input shape. So if you are relatively new to Python, this star variable idiom, it isn't a pointer if you're coming from C or C++. It is an idiom that means to unpack a tuple. So this makes our class extensible, so we can pass in a list of a single element, as in the case of the lunar lander and continuous lunar lander environment that we'll use today. Or later on, when we get to the continuous car racing environment, we'll have images from the screen. So this will accommodate both types of observation vectors. It's a way of making stuff extensible. And the new state memory is, of course, the same shape, so we just copy it. It looks like I am missing a parenthesis somewhere. I guess we'll find it when I go ahead and run the program. So, oh, it's not self.init, it's def. There we go. Def init. Perfect. So we'll also need an action memory. And that, of course, will also be an array of zeros in the shape of mem size by number of actions. I believe that means I need an extra parenthesis there. Yes. And we'll also have a reward memory, and that will just be in shape mem size. We also need a terminal memory. So in reinforcement learning, we have the concept of the terminal state. So when the episode is over, the agent enters the terminal state from which it receives no future rewards. So the value of that terminal state is identically 0. And so the way we're going to keep track of when we transition into terminal states is by saving the done flags from the OpenAI Gym environment. And that'll be shape numpy zeros, mem size, and I've called this float 32. It's probably because Torch is a little bit particular with data types, so we have to be cognizant of that. We need a function to store transitions, which is just a state, action, reward, new state, and done flag. So the index is going to be the first available position. So mem counter just keeps track of the last memory you stored. It's just an integer quantity from 0 up to mem size. And so when mem counter becomes greater than mem size, it just wraps around from 0. So when they're equal at 0, and when it's equal to mem size plus 1, it becomes 1, and so on and so forth. So state memory subindex equals state action memory index reward equals state underscore, and the terminal memory, good grief, terminal memory index doesn't equal done, but it equals 1 minus done. So the reason is that when we get to the update equation, the Bellman equation for our learning function, you'll see we want to multiply by whether or not the episode is over, and that is facilitated by 1 minus the quantity done. Just increment mem counter. And next we need to sample that buffer. So sample buffer, and that will take in a batch size as input. So the max memory is going to be the minimum of either mem counter or mem size, but the minimum. Then batch is just going to be a random choice of maximum index of max mem, number of elements, equal to batch size. Scroll down a bit. And then we want to get a hold of the respective states, actions, rewards, and new states, and terminal flags, and pass them back to the learning function. Sub batch, new states, rewards, it's not easy to type and talk at the same time, apparently. And let's get actions, self.action memory batch, and terminal good grief. So we want to return states, actions, rewards, new states, and the terminal flags. Perfect. So that is it for our replay memory. So you're going to see this a lot in the other videos on deep deterministic policy gradients because we're going to need it for basically anything that uses a memory. Next, let's go ahead and get to the meat of the problem with our critic network. And as is often the case when you're dealing with PyTorch, you want to derive your neural network classes from nn.module. That gives you access to important stuff like the train and eval function, which will set us in train or evaluation mode. Very important later. I couldn't get it to work until I figured that out. So, little tidbit for you. You'll also need access to the parameters for updating the weights of the neural network. So, let's define our initialize function. The beta is our learning rate. It will need input dims, number of dimensions for the first fully connected layer, as well as second connected layer, number of actions, a name. The name is important for saving the network. You'll see that we have many different networks, so we'll want to keep track of which one is which. Very important. As well as a checkpoint directory for saving the model. Also very important because this model runs very, very slowly, so you'll want to save it periodically. And you want to call the superconstructor for critic network, and that will call the constructor for nn.module, I believe. Input dims equals input dims, SU1 dims. So these will just be the parameters for our deep neural network that approximates the value function. The number of actions, a checkpoint file, and that is OS path join checkpoint dir with name plus underscore ddpg. And if you check my GitHub repo, I will upload the trained model because this model takes a long time to train. So I want you to be able to take advantage of the fully trained model that I've spent the resources and time training up, so you may as well benefit from that. So next up, we need to define the first layer of our neural network, just a linear layer, and that'll take input DIMMs and output FC1 DIMMs. We're also going to need a number for initializing the weights and biases of that layer of the neural network. And we're going to call that F1, and it's divided by 1 over the square root of the number of dimensions into the network. So self.fc1.weight.data.size, and that returns a tuple, so I need the 0th element of that. And then we want to initialize that layer by using t torch and then init.uniform underscore the tensor you want to initialize, which is fc1 weight data up from -1 to positive f1. So this will be a small number of order 0.1 or so, not exactly 0.1, but of order 0.1. And you also want to initialize the biases, bias.data, and I guess the same number. And again, in the future video when we go over the derivation of the paper, I'll explain all of this, but just for now know that this is to constrain the initial weights of the network to a very narrow region of parameter space to help you get better convergence. Perfect. So, oh, and make sure to subscribe so you don't miss that video, because it's going to be lit. So BN1 is a layered norm and takes FC1 DIMMs as input. The batch normalization helps with convergence of your model. You don't get good convergence if you don't have it, so leave it in. So FC2 is a second layer, another linear. It takes FC1 DIMMs as input and outputs FC2 DIMMs. Good grief. And we want to do the same thing with initialization. So it's 1 over the square root of self.fc2 weight data.size 0, and you want to do tnn init uniform underscore fc2 weight data minus f2 up to f2. Make sure that's right so we don't screw that up, because that's important. That looks correct. The syntax here is the first parameter is the tensor you want to initialize, and then the lower and upper boundaries. So next we need BN2, which is our second batch norm layer. FC2 DIMMs. And just a note, the fact that we have a normalization layer, a batch norm type layer, means that we have to use the eval and train functions later. Kind of took me a while to figure that out. Network is also going to a action value, because the action value function takes in the and actions as input, but we're going to add it in at the very end of the network. Linear actions C2 DIMMs, and this gets a constant initialization of 003, or sorry, the the next one, the output gets a initialization of 003, and since this is a scalar value, it just has one output. And you want to initialize it again uniformly. .q.weight.data, and that gets minus f3 up to f3. And likewise for bias data. Okay, so now we have our optimizer, and that will be the atom optimizer. And what are we going to optimize? The parameters, and the learning rate will be beta. So you notice that we did not define parameters right here, right? We're just calling it, and this comes from the inheritance from nn.module. That's why we do that, so we get access to the network parameters. Next, you certainly want to run this on a GPU, because it's an incredibly expensive algorithm. So the device, so t.device, CUDA 0 if t.CUDA.is available, else CUDA 1, so I have 2 GPUs. If you only have a single GPU, it will be else CPU. But I don't recommend running this on a CPU. So next, you want to send the whole network to your device by self.to self.device. We are almost there for the critic class. Next thing we have to worry about is the forward function, and that takes a state and an action as input. Keep in mind the actions are continuous, so it's a vector, in this case length 2 for the continuous lunar lander environment. It's 2 real numbers in a list or NumPy array format. So state value, so FC1 state, and then you want to pass it through BN1, state value, and finally you want to activate it. F.ReLU state value. Now, it is an open debate whether or not you want to do the ReLU before or after the batch normalization. In my mind, it makes more sense to do the batch normalization first, because when you are calculating batch statistics, if you ReLU first, then you're lopping off everything below 0, right? So that means that your statistics are going to be skewed toward the positive end, when perhaps the real distribution has a mean of 0 instead of a positive mean, or maybe it even has a negative mean, which you wouldn't see if you used the ReLU function for the normalization. So just something to keep in mind. You can play around with it. Feel free to clone this and see what you get. But that's how I've done it. I did try both ways, and this seemed to work the best. So next we want to feed it into the second fully connected layer. BN2 state value, and then we want to BN2 that. Oh, sorry, I already did that. One second, let me let the cat out. So we've already done the batch normalization. We don't want to activate it yet. What we want to do first is take into account the action value. And what we're going to do is activate the action through the action value layer and perform a ReLU activation on it right away. We're not going to calculate batch statistics on this, so we don't need to worry about that. But what we want to do is add the two values together. So state action value, f.ReLU, t.add, state value, and action value. Other thing that's a little bit wonky here, and I invite you to clone this and play with yourself, is that I am double ReLUing the action value function, so the action value quantity. So I do a ReLU here, and then I do a ReLU on the add. Now, this is a little bit sketchy. I've played around with it, and this is the way it works for me. So if you can clone it and get it to work a different way, the other possibility is that you don't do this ReLU here, but you do the ReLU after the add. So ReLU is a non-commutative function with add. So what that means is that if you do an addition first and then a ReLU, that's different than doing the sum of the two ReLUs, right? So if you take ReLU of minus 10 plus ReLU of 5, you get a ReLU of minus 10 is 0 plus ReLU of 5 is 5, so you get 5. If you take the ReLU of minus 10 plus 5, then you get ReLU of minus 5 or 0. So it's a non-commutative function, so it does matter the order, but this is the way I had to work. I've seen other implementations. Feel free to clone this and do your own thing with it. I welcome any additions, improvements, or comments. So then we want to get the actual state action value by passing that additive quantity through our final layer of the network. And go ahead and that. A little bit of keeping, we have save checkpoint function, and we'll say print, and then you want to call t.save self.state dict. What this does is it creates a state dictionary where the keys are the names of the parameters and the values are the parameters themselves. And where do you want to save that? You want to save that in the checkpoint file. Then you also have the load checkpoint, good grief checkpoint function, and that does the same thing, just in reverse. Loading checkpoint, and you want self.load state dict t.load self.checkpoint file. So that is it for our critic network. Now we move on to the actor network. That, of course, derives from nn.module. We have an init function, takes alpha, if we get spelled correctly, input dims, FC1 dims, FC2 dims. This is pretty similar to the critic network. It will just have a different structure. In particular, we don't have the actions. I can't type and talk at the same time, but it's pretty similar nonetheless. So input dims we want to save, and actions, FC1 dims, FC2 dims, same deal. Let me go copy the checkpoint file function just to make life easy. Perfect. I like to make life easy. So we have our first fully connected layer, and in that linear takes self.input dims as input and FC1 dims. And of course that operates in the same way as I discussed in the replay buffer, where it will just unpack the tuple. Next we have the initialization value, very similar, 1 over np square root self.fc1.weight data size 0th element, and we want to initialize the first layer uniformly within that interval. Init uniform underscore sc1 weight data minus f1 and f1. Copy that. That will be fc1 bias data. fc2 is another linear layer. Takes fc1 dims as input and outputs fc2 dims, as you might expect. And the initialization for that will be basically the same thing except for layer 2. So fc2 weight data, and then, you know what, let's just copy this, paste, and make sure we don't mess it up. fc2, f2, ooh, good grief, and plus minus f2, and that is all well and good. Other thing we forgot is the batch norm, and that is nn layer norm, and that takes fc1 dims as input. Likewise for layer 2, that is another layer norm, takes fc2 dims as input shape, and that doesn't get initialized, but we do have the f3, and that is 003. This comes from the paper. We'll go over this in a future video, but don't worry about it. Self.mu, mu is the representation of the policy in this case. It is a real vector of shape and actions. It's the actual action, not the probability, right? Because this is deterministic. So it's just a linear layer. Takes fc2 dims as input and outputs the number of actions. And we want to do the same thing where we initialize the weights. Let's copy, paste, and instead of fc2, it will be mu. And instead of f2, it is f3, as you might expect. Am I forgetting anything? I don't believe so. So finally, we have an optimizer, and that's, again, optim.addem, self.parameters, and learning rate equals alpha. We also want to do the same thing with the device. t.device CUDA 0 if t.CUDA.is available, else CPU, and finally send it to the device. That is that. So next we have the feed forward. So that takes the state as input. So I'm just going to call it X. This is bad naming. Don't ever do this. Self.fc1. Do as I say, not as I do. Self.bn1 of state. Value of X. That's a mistake. It should be X. X equals self.fc2 of X. bn2 X, and then X equal t.tan hyperbolic self.mu of X, and then return X. So what this will do is pass the current state, or whatever state or set of states, batch in this case, you want to look at from the first feed forward pass, batch norm it value, send it through the second layer of batch norm, but not activate, send it through to the final layer. No, I take that back. I do want to activate that. Silly me, f.value x, and then it will pass it through the final layer mu and perform a tangent hyperbolic activation. So what that will do is it'll bound it between -1 and +1, and that's important for many environments. Later on we can multiply it by the actual action bounds. So some environments have a max action of ± 2. So if you're bounding it by ± 1, that's not going to be very effective. So you just have a multiplicative factor later on. And then I'm going to go copy functions precisely the same. That's it for our actor. Next, we come to our final class, the meat of the problem, the agent. And that just gets derived from the base object. And that gets a whole bunch of parameters, alpha and beta. Of course, you need to pass in the learning rates for the actor and critic networks. Input DIMs, a quantity called tau. I haven't introduced that yet, but we'll get to it in a few minutes. We're going to pass in the environment. That's to get the action space that I talked about just a second ago. The gamma, which is the agent's discount factor. So if you're not familiar with reinforcement learning, an agent values a reward now more than it values a reward in the future, because there's uncertainty around future rewards, so it makes no sense to value it as much as a current reward. So what's the discount factor? You know, how much less does it value a future reward? 1%. That's where we get a gamma of 0.99. It's a hyperparameter. You can play around with it. Values like 0.95 all the way up to 0.99 are typical. Number of actions, we'll default it to 2. A lot of environments only have 2 actions. The max size of our memory, that gets 1,000,000, 1, 1 through 3, 1 through 3. Layer 1 size equals default of 400. Layer 2 size, 300 is our default. And again, that comes from the paper, and a batch size for our batch learning from our replay memory. So you want to go ahead and save the parameters, equal tau, and you want to instantiate a memory. That's a replay buffer of size, max size, input DIMs and actions. We also want to store the batch size for our learning function. We want to instantiate our first actor. Yes, there are more than one. And that gets alpha, input DIMs, layer 1 size, layer 2 size, and actions equals n actions, name equals actor. So let's copy that. So next we have our target actor. So much like the DeepQ algorithm, this uses target networks as well as the base network. So it's an off-policy method. And the difference here is going to be called target actor. It'll be otherwise identical. This will allow us to have multiple different agents with similar names. And you'll see how that plays into it momentarily. We also need a critic. That's a critic network. Takes beta, input DIMs, 1 size, layer 2 size, and actions equals n actions equal critic. So let's be nice and tidy there. And we also have a target critic as well. And that is otherwise identical, it just gets a different name. And this is sort of Q learning where you have Q eval and you store Q target, whatever you want to call it. Same concept. Okay, so those are all of our networks. What else do we need? We need noise. That's our OU action noise. And the mu is just going to be numpy zeros of shape and actions. So we'll give you an array. Zeros is the mean of the rewards over time. And next we need another function you may be able to predict if you've seen my videos on Q learning, which you should check out, is the update network parameters. And we'll call it with an initial value tau equals 1. So what this does is it solves a problem of a moving target. So in Q learning, if you use one network to calculate both the action as well as the value of that action, then you're really chasing a moving target because you're updating that estimate every turn, right? So you end up using parameter for both, and it can lead to actions. So the solution to that is to use a target network that learns the values of the state and action combinations, and the other network is what learns the polynomial. And then, of course, periodically you have to overwrite the target network's parameters with the evaluation network parameters. And this function will do precisely that, except that we have 4 networks instead of 2. Next, we want to choose an action. And that takes whatever the current observation of the environment is. Now, very, very important, you have to put the actor into evaluation mode. Now, this doesn't perform an evaluation step. This just tells PyTorch that you don't want to calculate statistics for the batch normalization. And this is very critical. If you don't do this, the agent will not learn. And it doesn't do what you think the name implies it would do, right? The complementary function is train. It doesn't perform a training step. It puts it in training mode, where it does store those statistics in the graph for the batch normalization. If you don't do batch norm, then you don't need to do this. But if you do with the other function, dropout. Dropout does the same thing, or has the same where you have all the eval and train functions. So let's start by observation into a tensor. D-type equals float to self.actor.device. So that'll turn it into a CUDA float tensor. Now you want to get the actual action from the actor network. So feed that forward to self.actor.device, and this makes sure that you send it to the device, so it's a CUDA tensor. So mu prime is going to be mu plus t.tensor. What are we going to use? Self.noise. That'll give us our exploration noise. And that is going to be D-type of float. And we will send that to actor device. And then you want to say, should be actor.train, shouldn't it? Yes, self.actor.train. Yes. And then you want to return mu prime. CPU.detach.numpy. So this is an idiom within PyTorch where you have to, it doesn't be the actual numpy value, right? It's tensor, which doesn't work because you can't pass a tensor into the OpenAI gem. So kind of a funny little quirk, but it is necessary. So now we need a function to store state transitions. And this is just kind of an interface for our replay memory class. So memory.store transition state action reward new state done. So now we come to the meat of the problem we're actually learning. So you don't want to learn if you haven't filled up at least batch size of your memory buffer. So self.memory.mem counter is less than self.batch size. Then you just want to return. Otherwise, action, reward, new state, done. You want to sample your memory. Memory.sample buffer, self.batch size. Then you want to go ahead and turn all of those into tensors. That's because they come back as NumPy arrays. In this case, we'll put them on the critic device. As long as they're on the same device, it doesn't matter. I do this for consistency because these values will be used in the critic network. So the dones equal t.tensor done to self-critic device. You need the new state t.tensor new state d-type t-float to self-critic device. You also need the actions critic.device, and you need states. t.tensor device device. And now we come to another quirk of PyTorch where we're going to have to set everything to eval mode. For the targets, it may not be that important. I did it for consistency. So we want to calculate the target actions much like you do in the Bellman equation for Q-learning, deep Q-learning. Target actor, dot forward, new state. We want the critic value underscore, which is the new states. So the target critic dot forward, and that takes target actions as input. So what we're doing is getting the target actions from the target actor network. In other words, what actions should it take based on the target actor's estimates, and then plugging that into the state value function for the target critic network. You also want the critic value, which is self.critic.forward for state and action. So in other words, what is your estimate of the values of the states and actions we actually encountered in our subset of the replay buffer? So now we have to calculate the targets that we're going to move towards, or J in range, self.batch size, and I use a loop instead of a vectorized implementation because the vectorized implementation is a little bit tricky. If you don't do it properly, you can end up with something of shape batch size by batch size, which won't flag an error, but it definitely gives you the wrong answer and you don't get learning. So target.append reward sub j plus self.gamma times critic value underscore sub j times done sub j. So this is where I was talking about the done flags. If the episode is over, then the value of the resulting state is multiplied by 0, and so you don't take it into account. You only take into account the reward from the current state, precisely as one would want. So now let's go ahead and turn that target into a tensor. Tensor target.to self-critic.device, and we want to reshape this. Target equals target.view self.batch size and 1. Now we can come to the calculation of the loss functions. So we want to set the critic back into training mode because we have already performed the evaluation. Now we want to actually calculate the values for batch normalization. Train self.critic.optimizer.0grad. In PyTorch, whenever you calculate the loss function, you want to zero your gradients. That's so that gradients from previous steps don't accumulate and interfere with the calculation. It can slow stuff down. You don't want that. So critic loss is just good grief. F.MSE means square error loss between the target and the critic